Good evening, everybody. It's Obi-Wan Piz for N Simplex Pachinko, and yeah, that was a weird little OBS thing popping up in the background. I don't know if anybody else actually saw it, but hey, whatever. I want to thank everybody for coming on into whatever stuff you come on into. Our math streams have been going pretty well. The gaming streams have been going, moderately well. And our YouTube channel has seen some steady growth. So thank you, everybody, for coming and seeing those. And spending whatever time you have to spare coming into our channels, wherever they may be, and listening to an old man ramble on. So, we have last stream we were talking about Peter Liljedahl's Building Thinking Classrooms, which is something that we are going to be analyzing over the next at least 11 more weeks, I think is how this is going to work, on Monday nights. So Monday night I'm going to try to dedicate more to like math education, and Wednesday night I'm going to try to dedicate more toward like math problems and teaching stuff. If anybody has any individual questions that you would like answered, if you have a particular query, whether that be education or actual math content, like, I don't care which night you ask. Go ahead and ask the question. I will always prioritize your stuff over whatever I have planned. In a way, we are here to serve, so we just want to get cool stuff, cool information and new ways of seeing the world out to all of you out there. So, tonight, we are planning on continuing our work with Calc 1 and talking about derivatives, specifically like the rules and particular functions derivatives. Cesar. Well, so there's like multiple ways to answer that, and sometimes that's the best way. So really early on, I watched a television program on PBS that was called Square One TV. It had a 15-minute segment that was based on just a bunch of fun little sketches, skits, things like that, and then another 15 minutes that was dedicated toward a mini show called MathNet, and they had 5 days a week that it was on. The first 4 had kind of the detective show formula, where it was like, we make some basic educated guesses, we go down wrong paths, we accuse the wrong person, etc., etc., and then on Friday was the big payoff where you catch the crook. Solve the crime, all that good stuff. So MathNet was interesting. Listening to Kate, and then later Pat, and George, George being a constant throughout the entire thing, played by Joe. Oh dear. Joe Howard. Hey, Path of Clarity. Good evening and welcome. Thank you so much for the follow. Yeah. So, yep, we'll get to that second. So, seeing Joe Howard play George Franklin, and then there's a whole host of other characters that are supporting, including James Earl Jones as their first like precinct lieutenant, whatever, chief of police. Um, so seeing all these people like work together and solve crime and like be mathematicians, like that was their actual job title, was mathematicians. I was like, oh, that's really cool. Like that's a thing. I kind of thought it was a little bit of a joke just because like they're on this TV show that is geared toward mathematics, so of course it's going to be geared toward that sort of thing. But then they kept talking with people who did like math as careers, and so it was really cool. Um, I watched that until I was probably 10, 11, 12, something like that. Okay, so it was on TV until I was about 10ish. um, and then I just kept watching it in reruns. Like, basically, as long as I was watching PBS, I was potentially watching MathNet or Square One TV as a whole, because I just thought it was cool. Even after it no longer was like really cool, because you start turning into a teenager and get all sulky and stuff. I was kind of like, you know what, this is a really good show, not just for like learning the actual thing itself, but also just like education as a whole, understanding the connections between things. It was really cool, and I kind of always like that. Around age 15 was when I had my first physical science class in high school, and that's when we had chemistry for the first half and physics for the second half. Hey Megalomorph, Square One TV and MathNet as its sub show. And it's all like on YouTube now if you want to go look for it. There's a guy, I think Anton Spivak is like the YouTube channel that has copied over almost all of it. And there's a few others that have ripped DVDs, which, like, PBS is unhappy that people have ripped DVDs on and put it online, but there's no real way to, like, purchase it from them. So, like, you can't have an alternative if there's no way to pay for it. Yep. So when I turned 15 and took my first real like physical science class, and we were doing physics for part of it, I had always been watching like Nova TV specials about astronomy and astrophysics, and like I didn't really like. I knew I loved space science, just generally speaking. Yeah, well. Please write your Congress people. So yeah, I'd always liked astrophysics and all this astronomy from like the little snippets out of books, and like I had like the Usborne science book, and I was like, I absolutely love like space science, and we went to the Museum of Science in Boston a lot, and like I'm always in the space science section longer than anywhere else, and like that should have been a clue. I took my physical science class in high school, and like my teacher was a science teacher, and she was really enthusiastic just in general. But then when we got through chemistry and we got to the physics section, she just like lit up. Her entire mannerism changed. She was like, we're on a physics now. Yeah, let's go. So I was like, this is it. Like, I'm pretty sure I actually want to do this for the rest of my life. And like, I can actually study this. I can actually do something with it. Let's figure out what we can do. And so I talked with her a bunch, and like eventually it came down to, you really ought to read, like, more general physics books, just like non-fiction, things that we know, things that we're working on, that sort of stuff. So my parents got me like Bryant Green's Elegant Universe. I got a few other ones that are in here. That one actually might be my wife's, now that I'm thinking about it, but nonetheless. Where'd it go? It must be here. It's got a gold cover. Like, how can I miss it? Blarg. Okay, well, it's around. Huh. Oh, there it is. Jeez. Yeah. Alright, so, let's see. This is 20... this is 2002, so this is a bit later. Elegant Universe... This one's 1999, so it was around the same time that I got The Elegant Universe by Byron Green from, I think, my grandmother. I got, let's see, I think my girlfriend at the time, sent me, or gave me, a copy of Zero by Charles Zive, and this has... Yeah, this is 2000. So we were still in high school. She gave me this to read and was like, I think you're going to really enjoy this. So I read it, and it's Zero, the biography of a dangerous idea. I was taking calculus at the time, I think. Yeah, like late 2000. And it's got just all sorts of really cool stuff about the mathematics of zero and like how it goes through... I'm not gonna, I'm not gonna... And then, when I was in college, he came out with a second book, Alpha and Omega, which is all about, like, the physics of all this cool stuff. But in high school, my parents bought me, for my 17th birthday, and I remember why, a copy of A Brief History of Time by Stephen Hawking. And this went through, again, like, what we know, how we know it, and the updated, so this is the updated 10th anniversary edition, which corrected some earlier speculation from 1998. Yeah, and then redone in 96. So my parents bought me this for my 17th birthday, and stuck in it as a bookmark was a set of 4 tickets to the Wang Theater in Boston. WGBH, that's the Great Blue Heron TV station, Boston, and ICEP, which I don't remember what the acronym is there, is doing a popular lecture by Dr. Stephen Hawking, October 7th, 1999. Whoops, I just doxed somebody. It's alright. And then, yeah, $58.50 per ticket. Well worth it. But it was for my 17th birthday, this book, and 4 tickets, all 4 of us, going to the Wang Theater in Boston to watch Dr. Stephen Hawking give a popular lecture. So, That's a very different kind of megalomorph. Let's just leave it at that. So anyway, absolutely loved it. It was most of what he was doing was kind of covered in here, so it was kind of like, okay, I sort of know this. I stood in line on my 17th birthday to watch Double Jeopardy, which was my first rated R movie that I watched alone, or that like I bought my ticket into, whatever. Yeah, that'll give you a bigger hint. Our local theater also didn't get first runs. It was like, they were like fifth in line. But I wanted to see a rated R movie on my 17th birthday, so of course. And I read, the first couple of chapters of this while I was waiting in line for tickets. So it was really cool, just overall experience. We went down to Boston. We went to a French restaurant, which was like just down the street from the Wang Theater, and had escargot, because my dad liked it, and he was like, I think you should try this even if you hate it. And I was like, all right. So I ate it, and I was like, that's actually pretty good, because it's just, if you like clams, it's not that different from snails. And we were very big, like lobster, clams. Lobster and clam, like, always go together. So you just buy a bunch of steamers, you buy a bunch of lobsters, you throw them in a pot and boil it. Right? Like, yes. Yes, it does. And, like, there's a little bit of a rubberiness to it, like calamari, right? So if you've ever had calamari sushi, then it's going to practically be all the same. Like, it doesn't taste any different. And especially if you put a huge amount of garlic and butter on it, it does. It literally tastes like garlic butter and a little bit of like rubbery texture to it, like clams and mussels and calamari. So so anyway, we went to the theater. It was great. He gave his public lecture, which was like 2 half-hour segments, I think, which did include a part on string theory megalomorph. And a bunch of stuff that he did cover in A Brief History of Time, but another year or two later, he came out with The Universe in a Nutshell. So I think that was kind of like his warm-up tour to throw this out here. Universe in a Nutshell is much more polished in terms of November 2001 is the date on that one. I think I got that for Christmas in 2001. And it's much more polished in terms of, like, it's got all sorts of pictures on all of the topics that you're doing. So it's a little bit more of a gentle introduction to the topic if you don't know it. And since I already did know pretty much everything that's in here, it was a good review, and it made sure that I understood what it actually was talking about, not like, making a bunch of misunderstanding, or not misunderstanding a bunch of it. So yeah, How the Universe Got Its Spots, I think, is my spouse's book, actually, by Jana Levin, who has been doing Star Talk for a while. We had Neil deGrasse Tyson, or opposite Neil deGrasse Tyson, so it depends on how you look at it and when everybody comes in. So he typically, Neil deGrasse Tyson typically does work with Chuck Nice, who is his friend, colleague, and not so much professional colleague in terms of physics, but a willing student and a colleague on the podcast circuit. Jana Levin is his professional colleague, who is a fellow physicist. And, like, they are two experts who work together a lot. They also have Robin Ince on, who, like, knows a fair bit amount of physics, but I think was a football coach or something like that. So it's kind of amazing, like how many people they all know. That one here and that one back here. Anyway, so once I got into physics in college, I took physics 1 and 2. In my first year, I was part of a studio calculus and physics class, which was, we were doing calculus-based physics, and at the same time, we were doing calculus-based physics, and our teachers taught all 5 days during the week. There was one physics lab and one calculus lab at some point during the week, and whenever they felt like it, they would just trade. So they'd trade off days for teaching. Maybe, your Monday calculus needed that Monday lab to do it, or maybe the Monday calculus wanted to wait until Tuesday lab, which was maybe a little weird, but in order to give it a day to simmer, or to do the calculus lab after you learn the physics behind it. So they traded back and forth all the time. It was kind of cool that happened. I actually got a 4 on the AP Calc exam, so technically I could have passed out of Calc 1 and gone straight to Calc 2, but they were like, well, if you do this Calc and Physics thing, they go together. It's probably, it's up to you what you want to do. And I was like, I think I want to take it so that I learn the integration of these topics a little better. Because I always felt like it was, I just felt like I always had a little bit of trouble understanding it. I talked about this last time or time before when we're talking about Peter Liljedahl. I was always a mimicker, right? I would take the information, I would go back to the examples, and I would try and look for a section of the homework that was very much like the examples, and then we'd just work on those kinds of problems. And this mimicking behavior is awful. It's horrible. Don't ever do it, please. But at the same time, it's potentially good if you don't know what you're doing to get your feet a little bit wet. I don't recommend it, because if you have an actual willing teacher around, it's much better to learn the deep set stuff, like the reasons why and the reasons behind everything. And this is through 15 years of teaching this stuff that I've come to this realization. Well, before that, but still. And like I said, it took until my sophomore year in college when I was taking differential equations, linear algebra, and multivariate calculus as one giant class for the entire year that I was like, this is not working for me anymore. I realized that I can't do this. I'm just looking at the examples and trying to figure out what's the same. No. You've got to start working on seeing the pattern that exists more than just being like, we're just going to get the pattern from the book. Don't do that. Don't do that to yourself. Well, anyway. I got through the end of Physics 1 and 2 as part of that studio class, and I said, the next class in line is thermodynamics, and it has a 39% pass rate, and I get the feeling that I'm not going to help that rate go up. So I was like, I'm thinking maybe I want to do something else. And we were doing the final major project that we were doing in our studio class. And one of the guys, we worked as all the physics majors together, because there were 6 of us or something like that, 5 in the same class. And they said, somebody was like, we're all just going to become physics teachers, right? And everybody kind of laughed about it, and I was like, I don't know if I see a problem with that. And it kind of sat there for a while, and the more I started thinking about it, the more I started realizing that like passing knowledge on to the next generation is the sort of thing that I felt like at the time I was interested in and potentially good at. Like I had no data to support the idea that I was actually good at it, but I was kind of interested. Hey, let's see where this takes us. So I went with it and changed my major in like the last week of the semester to math education at the secondary level. So that encompassed grades 7 through 12 was the intent, because in New Hampshire, 6th graders for the most part still went to elementary schools and 7th graders went to middle schools. In my hometown, we had 6 through 8 for just the hometown and 7 and 8 for all the sending towns, because we had a small enough district that there were 350-ish students in each graduating class. Probably about 400, give or take, when it was like that far back, from 6 towns. So this was meh. All right, it was Exeter High School, and Exeter, New Hampshire had about 100 on its own, and then East Kingston, Kensington, Brentwood, Newfields, Stratham. I think that's it. Total between all of us had another 250, and another 100 were from Stratham just by itself, because Stratham, New Hampshire is a large town. So Stratham and Exeter kind of were like the big ones, and then all the rest of us, again, East Kingston, Kensington, Brentwood, Newfields, all had like a class. I think our class in my school, in my elementary school, maxed out at about 28 one year, and that was only for part of the year anyway. One or two of the kids moved out to a different town, and so it was just like, well, we're not doing it anymore. We're back down to 24. They kind of juggled people around in districts and saw where they fit best. So, yeah, it was kind of interesting with the districts, because then I worked in Maryland, where like one city was broken up into 30 districts or whatever. I mean, it's just ridiculous. Okay, so that's a little bit about me. I taught at public schools for the first year and a quarter that we were down in Maryland. The quarter was the last quarter of the year, and then a full year after that. And then I was not interested in teaching in public school anymore, just because we were heading into some rough patches. I mean, we're seeing some of the worst aftermath of it right now. Politics between me and some of the heads of department at that last job that I was at, and the requirements of the education department. I was like, look, I'm done with my teaching certificate. I'm not going to get it. But I went to I went to the local community college, and I had taken 4 classes there to try to earn my teaching certificate. And I went there with a resume and said, I'm interested in becoming an adjunct professor. And they were all like, oh, that's great. Why don't you do the lesson, for this particular thing? Gave me like 2 weeks notice. So I planned a lesson on parabolic motion, all this other stuff with an applied problem at the end. I did the lesson, and they were very receptive and like, oh, this is really great. Cool. I think, you're going to be a great fit here. And I was like, oh, this is so great. Especially given that the last place that I was didn't really appreciate, the way I taught. So I learned how to teach over the next 10 years, basically, after that. And then we spent the last 5 trying to devise new methods of teaching and working on Peter Liljedahl's Building Thinking Classrooms, all sorts of really cool stuff. So it's been a really fun journey, and not particularly linear, which I will say is something that a lot of students don't really appreciate. Everybody kind of wants to get into their career and then immediately start working on it and staying in that career for preferably as long as possible. And it just didn't work. And it took me a long time to realize what the issue was. So, that's unfortunate. Come on, Spotify. You want to do the thing? Anyway. So that's how I got interested into and started working with math education. And when we go back in another 2 years, I'm probably looking to get into education policy. So we'll see how much I can fight for public schools and start making friends in all the districts. Because we're having some major issues in the United States. Okay, and then, come on, guys, what are you doing? And then to answer, path of clarity. So, technically I've got 2 names on the channel. One is me, that is Obi-Wan Pez, because my friend found a Pez dispenser that looked alarmingly like me. And so she was like, I have to buy this for you, obviously. And so that is like my name. I go by Obi a lot on many other people's channels. You're possibly going to hear of me here and there. But then N Simplex Pachinko is the channel name. So that's, everything that's here. What I'm going with there is I did a bit of math research when my second dean at the community college decided that he was going to, before he was dean, he started on a project to have our community college create a research journal. And this is a 2-year college, mind you, right? It is a community college. Our students are basically expected to get the basic idea of like how to do math and then move on to a 4-year university, and then toward the end of their senior year, maybe they'll do a research project. Maybe they'll wait until their master's or doctorate in order to actually do real research. And he was like, you know what? That's just not really how it's going to work. So we're going to start early and often and try to get our students into math research, doing something actual, literally good stuff, right? Some actual math research. So he had a lot of his students in the math proof class basically come up with a topic and start researching it. Just go. Like, it doesn't even have to be good. It doesn't even have to be particularly... Like, it basically just is... It has to be an open-ended problem. something that we haven't figured out yet, and why not, right? Do all the research, figure out what we figured out so far, where we are now, and what the next steps are. And every single semester he had 20 some odd students doing this. He ended up getting one of the other teachers doing this, or maybe two of the other teachers doing this, into it. And so they did it every single semester from then on. He started working on the research journal once some of his students actually started coming back with, like, stuff. It wasn't necessarily a finish to the problem, but it was something that moved the needle just a little bit. Something that moved the ball forward, if you will. So we ended up calling it the Journal for Research in Progress. And JRIP at our community college. And it, helped the students figure out how to actually do math research. It also got some other students involved when we started recruiting from other departments as well into making a research journal. So, like, how do you do that? And the whole process we started, like, outsourcing to the students and just being the advisors in the background, making sure that all the work is getting done and, helping where necessary. But, like, for the most part, it started being student run. We're like, this is pretty much what we want. Like, we were the advisors. We were the editors. So we also went through and edited everybody's papers at the end and made sure that they were cleaned up and everything. But all the individual advisors went through and individually made sure that their papers were good enough to publish before submitting. So there was a lot of really cool stuff that went on with our Journal for Research in Progress. And I did a little bit of work myself on one particular source of research was the Pascal triangle, and specifically dealing with the what's also known as the 3-simplex. So doing a Pascal triangle in 3 dimensions. So tetrahedron. You start with one particular location all the way at the top, and then we think about, like, if we now connected this in 3 dimensions, you would have 3 different possibilities for how an object would be able to fall through, like, if you think about how it works in 2 dimensions, right? Let's start there. It's a plinko board, pachinko board. Sorry, plinko is a registered trademark. Can't do that. It is a pachinko board. So you set a ball going at the top, it hits a little peg, and then it has one of 2 possible ways to go, left or right. And then it falls onto the next peg. And based on its momentum, velocity, all the other good stuff, once it hits the peg, which way is it going to go, left or right? And on average, if you restrict the movement of these things enough so that their momentum essentially becomes downward, so that they hit the peg essentially right in the middle, right? Essentially right in the middle, then you have the possibility for each of the directions to be 50-50, or at least as close to 50-50 as we can make it. If you drop a ball in 3 dimensions, it will hit the center of 3 either cylinders or hexagonal prisms was our favorite. It will go into one of those 3, right? It will go right through the center, hit the center point, and then drop into one of the 3 tubes that you have there. Prisms, whichever one you're using. So it has a 1 in 3 chance of going in each of the 3 directions. And then when it drops through that one, it hits another one, which has a little nub on it, which in theory should drop it in one of three directions again. So his students calculated the full 3-simplex of like what is each value going to be as we drop through this pyramid. Then they discovered a few interesting things. One was if you slice off the face of the pyramid and set it aside, then you now have a smaller pyramid, smaller, by one row, or by one... You can't call it a row or a column or whatever. So you take one edge off the face, and now you've got a slightly smaller pyramid. And now, if you look at the numbers that are in those spaces, then they also make a Pascal triangle, but it's slightly altered. So on the front face, that's just the Pascal triangle. On the second face, they're all multiplied by a constant. If you slice off the next face, it's a Pascal triangle, but multiplied by a linear value. So it increases as it moves through. And we saw this, and we're just like, this is something. Like, we just keep cutting faces off this pyramid, and you keep getting an increased polynomial multiplied by the original Pascal triangle. So that was really cool. And while his students were working on that, I was slicing the other way and saying, if you only look at the slice going going across one row at a time, then these are the numbers you're going to get on each of these rows. And the interesting thing is that, at least the interesting thing to me, was that if you take all those values and add them together, we're going to get an increasing value as you keep going down. However, the ratio between the sums on each individual row ends up being asymptotic. And so I was like, that's what I want. And so I started hunting it. And when I did it with... so I did it with the original Pascal triangle. And like, you just take all of your successive rows and you find the sum going all the way across. And then you say, what's the ratio of all these things? And it's a fairly easy number to find. I won't give away too much here. But then I was like, so if we add not just the numbers directly above, but also like the numbers that are 2 spaces away from however you got there, and add all those numbers up. Now it's not independent anymore, right? Because you're adding stuff that was already added. So it's a little weird. But when you add those up, you get a different ratio between the rows, the sums of the rows. And then if you add more rows to get to each individual value, you get different ratios over and over and over again. And again, when I did what was called I started calling them like the like Fibonacci, where you were adding the 2 rows previous to get the next row. And Fibonacci, you add the 3 rows above it to get to the next row, rather than the original Pascal triangle. You're just adding the rows above to get to the new place. When I started adding literally everything that it's connected to going all the way to the top, I call that the Infinitacci. So we're always just going to keep adding everything that any individual is then connected to above it. So we just add all of those values together. Interestingly enough, the outer edges of the Pascal triangle, when you do it Infinitacci style, become powers of 2. Which maybe I shouldn't have been surprised at, but it basically becomes, what's the sum of all the numbers above it? Which ends up becoming powers of 2 as you build that. So when I found the Infinitacci triangle going all the way through, and then the sums going across every row, I found out that those have a ratio, those sums have a ratio of, I believe, 1 plus the square root of 3. And I looked at the decimal approximation and I said, I know what that is. Because I've been doing trig for like, I've been doing trigonometry for the past 10 years. So of course I know what this number is. Why don't I understand? Like, why can't I figure out what this number is just offhand? And then I finally looked at, like, just plugged it into my calculator. It was like, that's the same decimal expansion as the square root of 3. Like, the square root of 3 and this number have the same decimals. It's just the whole number is different. So 1 plus that. And so I felt really big brain at the moment. I don't know if anybody has ever done that particular thing. And then I wanted to say, okay, what happens if we expand this into higher dimension space? So if we expand this into, the 3 simplex, the 4 simplex, the 5 simplex, what are we going to get? Is there going to be a location when we start doing these, Infinitacci style things and end up getting a ratio that is a particular constant that we're going to be able to find? And, like, what constant is that? And I unfortunately was trying to figure it out, like in Python and stuff like that. How can I do this particular programming? And I kept getting lost, and I was like, well, maybe I might need like tensor calculus in order to figure this out. I don't think I actually need tensor calculus, but it might make it easier to do some of the notations. But yeah, I've gotten lost over the years and haven't actually finished it, which is too bad, but we'll see what we can do. Anyway, maybe we'll actually do some work. I'm sure people have come and gone because I am not doing what I said I was doing. Alright, everybody. Actual Calc 1 stuff. So anybody who sat and listened to that, thank you very much for indulging the ramblings of an old man. We'll see what we can do with this. Alright. It's a raiding party. Hey Zach, how's it going? Anybody who came in with Zach, my name is Obi-Wan Pez. This is N Simplex Pachinko. You just missed the long rambling of why I got into math education and how my channel name got chosen. So, yeah, good news, I guess. You missed all that. Isn't this Twitch? Yeah, I mean, true. But then we literally did nothing for the last hour in this Calc 1 stuff, so, Okay, so last time we were talking about, and for anybody who came in, we're talking about derivative rules in Calc 1. We're generally speaking doing work on cracking the GRE math test. This is the math subject test for the graduate record exam. If you are not interested in taking the graduate record exam, i.e. you're not going to grad school for mathematics or similar field, or you have no interest in listening to the ramblings of another mathematician, feel free to catch the VOD some other time. We also have a YouTube channel and and we do gaming on this channel as well. So Monday nights, lately, we have been doing math education and talking about different methods of teaching. Specifically, we're working currently on Building Thinking Classrooms by Peter Liljedahl. Both Zach and I have read into it at the very least. I attempted it for a semester. I mean, I sort of attempted it for like 2 semesters, but it was shaky. I actually really went for it hard one semester, and like methodically it worked. In my particular record-keeping style, it had mixed results. I highly recommend that anybody who's actually going to be interested in learning about this style, learn as much as you can about it and really go hard in terms of trying to get everything to work properly. It's going to require a lot of work. But it's interesting. In addition, on Wednesdays, we do... on Wednesdays, we do math. So we will be doing more calculation end of math education, where I'm going to work on teaching particular subjects. If anybody's interested in giving input as to the which subjects you might want to see, we do have a I don't suppose that this is working yet, but nope. We do have a Discord server where a number of us math education types end up going. This is The Elements, the server from Penn Center. And boop. Anybody who wants to join, you can join there. Anybody who's here on a VOD, you can feel free to come in any other time and ask one of the math people for a invite to Penn Center server. We also have many other friends, and anybody else who was here and does not yet know Zach, please rectify said situation. E to the 2i pi, also known as Zach, has been a friend of the channel and math friend for a couple years at this point, and has been instrumental in trying to get multiple math people together and try to share ideas and yeah, just be cool. Okay. Additionally, on Fridays we do our gamey streams, which currently we're working on Against the Storm, which is a civilization type city builder, and also a Age of Empires 2 sort of city builder, both at the same time, and uses prestige currency to help you build faster as you play further on. So it's also a roguelite. Wild. At some point, yeah. I know, my kids are like, haven't you finished this? I'm like, nope. I'm waiting. Right, and then on Tuesdays we just finished a game called The Swapper, and I'm pretty sure next Tuesday we're gonna go for we're gonna start 9 Souls, which I was unaware what kind of game it was when I started playing, and I was like, oh, this is maybe this is fun, and I needed to do it for to watch a Jacob Geller video because it was on there. It was potentially spoilerific, and then I was like, actually, this is probably a good stream game. So we'll be doing 9 Souls for multiple reasons. Yeah, I mean it's been about a year since we last played it. Let's see. And then any other day of the week we feel like playing games, we also feel like playing games. So one day, either Saturday or Sunday, we dedicate to Satisfactory. And sometimes on Thursdays we do Elite Dangerous. Kind of depends on how we're feeling. So we'll see you all out there in whatever capacity you would like to come and see us. So last time we talked about taking the derivative of sums. Oftentimes we utilize square brackets just as like, you know, this is another set of parentheses that I don't necessarily feel like putting down as round brackets. Right, last time we also said if you take the derivative of a constant times a function of x, then we're also going to get here the same as a constant times the derivative of a function of x. Right, and we went through and actually proved how to do this using the definition of derivative. So the definition of derivative is when we're taking a derivative of a particular function, f of x, then what we're going to get is the limit as h goes to 0 of f of x plus h minus f of x all over h. This is really x plus h minus x, but come on. We're not gonna make you do all that. Right, so essential points here, we were talking about limits. We were talking about the fact that this is the slope formula. This is the difference in your y's, or the function values, divided by your differences in the x's, or the distance you have traveled in the x direction, h. And when we look at the limit of this particular motion going to 0, we essentially are building from a secant line which looks like this, to building a tangent line which looks like this. Get rid of that sloppiness. What? Honestly. Right, so here we have right, h goes to 0, whereas here we have a secant line when h is greater than 0. I guess technically it could be less than 0 as well, because we could be going in either direction, but we could also just reassign where we're moving to. So h is a constant value that is not 0 itself. And the tangent line is as h is approaching 0, because it can't be 0 itself, again, because here we've got it in the denominator, so it doesn't really work that way. Okay. We're going to do product rule, quotient rule, and maybe chain rule before the adds start. We can totally do this in 5 minutes. Yep, 100%. Guess technically we got 10 minutes now. All right, if we take the derivative of a product of functions, so f times g of x, then we want to look at what that's doing. So limit as h approaches 0 of f times g of x plus h minus f times g of x all over h. So this kind of seems to be a problem in that we've got a lot of terms in here which really can't be separated all that much. However, if we introduce new terms, so we separate all this stuff out. We also then do add f of x plus h times g of x minus the same f of x plus h times g of x minus f of x times g of x all over h. And from here on out, I'm just going to use 1 over h as a multiplier on the front, because this is going to be onerous otherwise. All right, 1 over h times the quantity. From the first two terms, we can take out f of x plus h, and then we're left with g of x plus h. Swap them. All right, minus first, plus second. You'll see why, if you don't already. Right? G of x plus h here. Wait, no. G of x plus h minus g of x. Okay? And then in the second group, we have a common g of x with leftover f of x plus h minus f of x all over h, again multiplied by 1 over h out front. Then what we can do is separate stuff. So we have the limit as h approaches 0 of, the first group is f of x plus h times g of x plus h minus g of x all over h, because again, multiplied by 1 over h. The second group becomes plus g of x. Actually, let's, in fact, move that. Plus the limit as h goes to 0 of g of x times f of x plus h minus f of x all over h. Okay? And then when we look at this, we can see that the limit of x, limit as h goes to 0 of f of x plus h can just be f of x. That's it. By the limit rules, we can also then introduce the limit into the second part of the product, just by itself. So now the limit as h approaches 0 of g of x plus h minus g of x all over h. Hey, that looks an awful lot like the definition of derivative, because it is. Right? F of x times the derivative of g of x. Plus, the limit as h approaches 0 of g of x is just g of x. And again, here we have a multiplier of the limit as h approaches 0 of f of x plus h minus f of x all over h. Which is again, now this is g of x, multiplied by the derivative of f of x. And if you would prefer, you can write this as, for instance, f prime of x times g of x plus f of x times g prime of x. Again, that originally was, hey, let's take the derivative of the product of f and g as functions of x. So there we go. There's your product rule. Same one that you learned in calculus class. So here, in order to do this, we just said, okay, take the definition of derivative, put the product rule in there, f times g, sorry, the product of these things, f times g of x plus h minus f times g of x all over h. And now we're going to split all this stuff up by introducing new terms, f of x plus h and g of x multiplied together, and then have that be plus and minus. It's easier if you just have opposite signs for these things, so plug them into the appropriate places. And if you went the opposite direction and did f of x times g of x plus h, this works just the same. You just end up getting a different order. So, and order does not matter in this particular case. We end up with a commutative, several commutative terms, right? Our f prime and g and our f and g prime can be multiplied in either order, and the groups can be added in either order. That doesn't matter. That's all good. Okay, what about division rule? So when we have a quotient of these things, we get the limit as h approaches 0 of f over g of x plus h minus f over g of x all over h. Again, similar type stuff. Here what I'm going to actually do is multiply. Am I? Yes. Multiply both top and bottom by g of x plus h times g of x. All right, when we do that, we get the limit as h goes to 0 of f of x plus h times, we just had g of x plus h that got multiplied out of this denominator, so now we've just got g of x here. Minus, same thing here. This is going to be f of x times g of x plus h. Same deal, g of x got multiplied out. Divided by h times g of x plus h times g of x. All right, this doesn't quite work in the exact same way as the other one, at least not from this particular form. Ads are going to start in 20 seconds. Let's give us another 5 minutes here. We're just going to burn all of our delays. It's fine. I think we can do it the same way. So if we had that up above for the product rule, right? Where we had sort of, right? Because both of the left ones were x plus h and both of the right ones were x. I don't think it actually matters. I think in this case we could do the same thing and end up getting something slightly different. However, the thing that we're adding is going to change. Right. This is how this works. Been a while. All right, we're going to add f of x plus h times g of x plus h. And again, we're going to subtract first, add second. fx plus h times g of x plus h. Okay, switch color, move over, and then this is minus f of x times g of x plus h. multiply by 1 over h. Because again, I have no patience. Equals limit h goes to 0 of first two have a common factor of f of x plus h, and then have a, you're going to like this, g of x minus g of x plus h all over h. And next ones have a common factor of g of x plus h times f of x plus h minus f of x all over h. And again, limit h goes to 0. We're going to do the same thing as above. So the f of x plus h as h goes to 0 is just f of x. Ah, wait. Hang on. This is still all over. It's fine. It's fine. This is still all over g of x plus h times g of x. Ugh. This is fine. Don't worry about it. Fine. We'll just go all the way across. Right? And then all of it is multiplied by 1 over g of x plus h times g of x. So again, first group is f of x plus h. We take the limit as h goes to 0, and it's just f of x. We take the limit of the this thing, which is the definition of derivative of negative g of x. Right? Or you could factor out the negative and then say it's the derivative of g of x. That's fine. It doesn't matter. Okay. And then we have over here the limit as h goes to 0 of g of x plus h times g of x is going to be, we'll make this just all negative first, and then say that this is going to be f of x times the derivative of g of x all over the limit as h goes to 0 of g of x plus h times g of x is g of x parentheses squared. Right? Where it's convenient, we could just sort of move it along. It's fine. Okay, we're going to get ads in 15 seconds, so just to let you know, we're not going to be able to finish this just before break, but we'll do it just after. And wow. Right? This is working great for us. All right, see you in 3 minutes. Hell yeah. Be right back.
There's more to Spotify than meets the ear. That's because video is taking center stage on Spotify, with over 300,000 video shows and 300 million users already watching their favorite podcast. With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify, turn views into fans, and monetize your passion.
Tear us apart and bury me, all in my head alone. Calling your name but only feel the cold. I sense the change in energy, all of my fuse is blown. If as design, building a bonfire. So how do we end up here? Could have sworn we said forever. Hopelessly I keep on losing myself, with the flames getting higher, all of the problems that I couldn't help. Oh, I'm building a bonfire. Hopelessly I keep on losing myself, with the flames getting higher, all of the problems that I couldn't help. Oh, I'm building a bonfire.
Alright, good evening and welcome to anybody who's new, anybody who's used to seeing my face around here. We're working on the GRE, Graduate Record Exam Math Subject Test, which is just an interesting source of problems to be able to go through. We're eventually going to work our way through Calc 1, Calc 2, Calc 3, differential equations, linear algebra, eventually all the way up to topology. So I never actually took topology, so that ought to be interesting. I can't imagine it would be, like, horribly difficult, but at the same time, it's been a while since I've, like, self-taught anything. So we'll see how it goes, and if we need desperate help, we will possibly call on our friends like Zach at either 2iPi, Penn Center, or many of the other people who may have taken topology and try to get through it. I get the feeling I'm going to be able to do, like, you know, a good portion of it, but at the same time, like I said, I've never taken it. Which is really too bad, because I think there's a topology book, like, right here. Maybe not. Yeah, my spouse took it. I think she might have left it back in Maryland. Or I left it back in Maryland, I guess. It's the more appropriate summary. Maybe. Might have it. We'll see. Okay. So we worked out proofs for both the product rule here, wherein, again, if we just do the standard definition of derivative with the product of f and g, and then we add in terms which are minus and plus f of x plus h times g of x, i.e. that they have different inputs. So one of them is x plus h, the other one is x. And it doesn't matter which one, as long as it's plus and minus the same thing, right? Then introducing those terms allows us to factor stuff out, get two terms which are the definition of derivative, and we, I don't want to say distribute because that's not true, but we give the limit of propagate, I guess is the better word for it. We propagate the limit as h approaches 0 to all of those terms. We get the definition of derivative for g and for f, and then we end up having, again, our standard definition that we always know from product rule. When we do quotient rule, we do almost the same thing. We start with the quotient of f and g with, again, the appropriate inputs, x plus h and just x. And then we multiply both top and bottom by g of x plus h and by g of x. In doing so, we eliminate one of the terms, namely the ones that are in the sub-denominators, right? The compound denominators. And then we effectively propagate those g terms to the bottom, as well as the remainders here. So g of x in our first term, and g of x plus h in our second term with f of x. And then we add and subtract the same thing, but this time, since we have differing inputs, we have them be same inputs. So both of them in this case are x plus h. And in doing so, again, we factor out whatever terms we have as common factors, and we end up with the definition of derivatives again, but this time it is the definition of the derivative of negative g of x, or negative the definition, or negative the derivative of g of x. So your choice how you want to do that. That also works because we said from last time that if we have the derivative of a constant times a function, then that constant can come out. So we're okay with that. And then we have, again, that negative can pop out, and then the denominator has the limit as h approaches 0 of g of x plus h times g of x. Here, this is just going to approach g of x parentheses squared. Right, saying that h is 0 doesn't break anything here, so that's okay. We can do that. And then we have our derivatives with the appropriate f and g in the appropriate places, the negative in the appropriate place. They both have a common denominator. Bring them together, and we get the standard definition that we're all used to. F prime times g of x minus f times g prime of x, all over g of x squared. My favorite way to actually work with this is to start with the power rule and go from there. But this actually doesn't have the power rule right here. Yeah, it just gives it to us later. Hmm. Hmm. Right, using the power rule. Doesn't give us a restriction on it, does it? No. Cool. So this becomes a little bit of a problem. Right, this is going to... Nope. Limit. If we just look at the generic function and have it doing this, then we do have a small issue. Namely that, like, depending on the function we have, raising it to the nth power is going to have potentially different results. So this doesn't really work for us just yet. However, d of x to the n, so the derivative of x, any x to the n, normally we like to say that n has to at least be like rational, but turns out that it's not even necessarily true. It is, however, easier to say that when we're looking at how to do this, if we just restrict for the moment n to be an integer, then this makes it a bit easier to work with. So we're going to get x plus h raised to the n minus x to the n all over, and that is limited. Limit h approaches 0. All that stuff over h. Right, if we expand this, this becomes a binomial expansion. Right, and it's a binomial expansion on x plus h. So if we know our binomial expansions, awesome. If you don't, it's the n simplex, by the way. So it makes it a lot easier to work with when you actually know your Pascal triangle and all that stuff. Okay, so here the first term is just going to be x to the n. Plus the next term in, right? If we had x plus h squared raised to the second power, then the next term, the middle term, ends up having us, with x squared plus 2x to the first h to the first. When we do third power, it's going to end up being 3x to the second h to the first. So it always ends up being that this is going to be n times x to the n minus 1 times h to the first, plus the second term in ends up being, or second in anyway, ends up having two numbers that are multiplied together. And realistically, there's an easier way to do all this. It's actually to say that all of this is based on the choose function. So our first number is n choose 0. So we have chosen in a stack of n x plus h's, right? As many as you need to pretend. We have chosen 0 of them to be h's. So what do we have? We've chosen every single one of them to be x's. Therefore, there are n x's all multiplied together. Therefore, x to the n. Okay, the next one is what happens if we have n blocks of x plus h, and we choose one of them to be h. Right? This is n choose 1. So there are going to be x to the n minus 1 x's and 1 h. And again, next one down, what happens if we have n x plus h's, and we choose 2 of them to be h? Well, that's going to be x to the n minus 2 times h squared to the second, plus dot dot dot. This is going to be multiplied all the way down to n choose n minus 1 x to the first h to the n minus 1 and plus n choose n. We have chosen all of them to be h's, so that means we have no x's and all h's. Okay, minus this x to the n term, which comes from here. Right, so this is our binomial expansion. Okay, so we got all this stuff. Cool. Well, that means that we're going to have n choose 0 is 1, n choose 1 is n, n choose 2, it starts getting slightly harder from here. But the idea is that we've got right, the choose formula. Oh, man. The choose formula works as... Oh, no. Hang on. 2 factorial over... nope, not 2. N factorial, n minus 2 factorial. That feels wrong. Yeah, that feels too small. Oh, n factor. Yeah, okay. N factorial's on the top. Woo! The number of things you're choosing from, factorial, over 2 factorial, n minus 2 factorial. Right, so this is going to end up being n times n minus 1 times n minus 2 factorial over n minus 2 factorial is just going to get those to go away over 2 factorial. Here it's a 2. And, if you think about it, right, one of these numbers, either n or n minus 1, has to be an even number, so it's going to divide nicely by 2, which is 2 factorial. All right, we can make the same argument with all of the other numbers going on down, right? 3 factorial has both a 3 and a 2. One of them must be divisible by 2 because now we've got 3 numbers in a row, n, n minus 1, and n minus 2. At least one of them has to be divisible by 2, and at least one of them needs to be divisible by 3. Right, so all of these are going to end up cleaning up super nice. This one here is going to be n factorial over n minus 1 parentheses factorial times 1 factorial. They've changed positions, but this is the same as what was going on with n choose 1, right? N choose n minus 1 is the same as n choose 1. And then n choose n is going to be n factorial over n factorial 0 factorial. 0 factorial is 1, and n factorial over n factorial is 1. So this is just equal to 1. All right, point being, all of these coefficients out front are going to be whole numbers. And we can see that in the Pascal triangle if you've ever done any work with it. All of those coefficients out front are all going to be integer numbers. It works out very nicely. And if you don't believe me, please feel free to go for it yourself, right? All of those factorials are going to end up with whole values. All right, now they're all multiplied by 1 over h. So what does that do? Well, that's going to decrease the magnitude of all the degrees. All right, x to the n minus x to the n is just 0, so that's gone. This is going to be n times x to the n minus 1 times 1. Plus n minus 1 all over 2 times x to the n minus 2 times h now to the first. Plus n times x to the first times h to the n minus 2 plus h to the n minus 1. Well, now we can take the limit without this becoming an indeterminate value because the first term has no h's. So this is going to be n times x to the n minus 1 plus all of this stuff has h's left over. It's now 0. And QED, right? The derivative of x to the n is always therefore going to be n times x to the n minus 1. All right, this is the power rule. And as long as it holds for n, the binomial theorem, sorry, as long as the binomial theorem holds for n, this is always going to work. So it doesn't matter what n is. It can be any real number. And you won't be able to prove it in quite the same way. But you will at least be able to say, hey, look, this is how it works. You know, here's our binomial expansion. Right? Show the binomial expansion, how that binomial expansion ends up leaving h's behind, and then it eliminates the first term. So again, you end up with just n times x raised to the n minus 1. All right, quotient rule here. Right. So my favorite quotient rule, proof, is to say that f over g, we want to take the derivative of this again. And this is going to be the derivative of f times g of x raised to the negative first power. All right, f of x times g of x raised to the negative first power, or, you know, 1 over g of x. Keep in mind, this is a power, not the inverse. So here we have a product rule. We'll deal with that first. So we end up with f prime of x times g of x to the negative first plus f of x times the derivative of g of x itself raised to the negative first power. I guess we do have one more thing to talk about before we technically finish this one. However, we can also kind of just, we'll see it. All right, this is f prime of x over g of x plus f of x times negative 1 comes down. We're multiplying by that g of x that we had before raised to now a negative n minus 1 power. So here this is going to be negative 1 minus 1. Okay, now we do technically have one thing that I've been leaving out this entire time, which is that over on the right-hand side, normally what I would have been writing is that all of these little things, rather than doing the primes, rather than whatever, normally we'd be writing that we want the derivative of each of these individual functions. So we end up with, you know, this d of f of x and the d of negative g of x here. We're just kind of saying, yeah, we're taking the derivative of the function itself as we're doing this. So we have not technically addressed this here, nor have I supported it with notation here. However, Right, what I should have probably had here was there is also a dx. Just like with everything else we've done, like all of this persists throughout. But we've been using definition of derivative, so I was like, oh, well. Or here, right? We could call this like df is equal to all this other stuff, dx. Which is also why most times when we deal with derivatives, we're talking about df dx, the derivative of f with respect to x. All right, now, looking at this, we've got f prime of x times g of x would give us g of x squared in the denominator, which I'm doing this as a preventative measure because we know that this is going to have a negative 2 as an exponent, so it's going to bring it down into the denominator. We're going to have a minus, we're going to have an f of x times bracket, nope, that's elsewhere, f of x over g of x parentheses bracket whatever squared, and then times dg is going to be our g prime at x up top. Again, this is getting slightly pedantic in that realistically this should end up with a dx at the end. Way over here. Actually, right, it doesn't technically create it until get this stuff going. So that requires a dx. That requires a dx. Here, we build in the dx where the dg appears, and then here we factor it out from everything. Again, pedantic, but becomes kind of necessary at some point when you're doing especially analysis to try and show where all of these terms come from. Anyway, so this is my favorite proof of this is my favorite proof of the quotient rule because it utilizes both of the pieces of our power rule and also our product rule that we had up top in order to figure all this out. Right, so then if we have like functions of other functions, right, this becomes a little bit of a problem. Because now we say, well, what do we do with what do we do with all like the what do we do with all of the internal functions when we take the derivatives of the external functions? So that's not it. There we go. Let's back up to Calc 1. Right, where do we get... Oh no. Oh no, I stopped naming them at some point. Oh, that's awful. Almost. I was a day off. Not too bad. Okay, there's chain rule. Okay, so I'm coming at it from a slightly different perspective, but it's the same deal. Okay, so there's kind of two ways to go about this. When you take the derivative of f of g of x, what we have to see is that first we're taking the derivative of f with respect to g. Apologies, that should not be like that. Someday you'll find out why. Okay, so here we're taking the derivative of f with respect to g, but now we also have to take the derivative of g with respect to x. Okay, an alternate way of looking at this is that we're taking the derivative of f with respect to x, but there's like this g thing that's getting in the way. So we have to take, right, df dg in order to take the derivative of f with the shape of whatever else it's in, which we call g, and then we have to say, okay, now we take the derivative of g with respect to the next variable in. So when we're looking at something like this, we would say like f of x is, well, f of g of x, right? The function we're trying to take the derivative of in the first place is x minus 3x squared plus 2. That's a terrible idea. Whatever. All right, x squared minus 3x plus 2 parentheses cubed. So f of x is equal to x cubed. And g of x is equal to x squared minus 3x plus 2. Right, so decompose it into its parts. And then we say, if we're going to go about finding the derivative of f, right, which we could, in theory, just say that, well, this is just the whole function f, right? Sure, originally it might have been given to us as this stuff in parentheses, you know, quadratic in parentheses raised to the third power. That's f of x. Well, we can choose to decompose it. into multiple parts and say that this f is really just going to be f of g of x, where f of x is the big x cubed on the outside, g of x is going to be the x squared minus 3x plus 2 on the inside. We could have chosen to do this differently, but I think you all probably get the idea more or less at this point. If anybody does have any questions, please bother me. Throw questions out there until you get sick of me, because I'm not going to get sick of you. Just trust me. So the first part is df/dg, which is going to end up being a product or a power rule of x cubed. So the x cubed power rule is going to be 3x squared. Or I suppose we could back this up. Let's back it up even further. Let's turn this not into g of x, or f of x, but rather f of g. So that's g cubed. This makes it way better. And then our next function down is g of x, which is x squared minus 3x plus 2. This is easier to visualize it, even if it doesn't... yeah, it's just easier to see. So here, df/dg is going to be taking g cubed and taking its derivative with respect to its variable g. So this is going to be 3g squared. But df/dx needs to be then df/dx like this, such that we fill in the blanks now with dg over dg, which then allows us to say, this is going to be df/dg, which is 3g squared, times dg dx is now, what do we get when we take the derivative of g of x, right? dg dx is equal to, it's a power rule, x squared becomes 2x to the first. Negative 3 is a constant, so it doesn't change. The derivative of x, well, that's x to the first. So the 1 comes down, and the power ticks down from 1 to 0. So now x to the 0 is just 1 times the negative 3 that was already out front. All right, and then here, if you wanted to, we could also make that 2x to the 0. And when you've got x to the 0 comes down and multiplies it and knocks the whole thing out. Right, so dg dx is now 2x minus 3. Right, and then we can't leave it in multiple variables. That doesn't work. We want df/dx, which is then going to be 3g, the original g was x squared minus 3x plus 2 squared times 2x minus 3. Right? So if anybody has any questions on this, please let me know, because again, this is what's called this is what is called the chain rule. And it doesn't matter how long the chain is, we just keep it going until we run out of functions to talk about. So we end up with f of g of h of j of k of m of x. 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, 0. Cool. And if we want to take d dx of all of this, right, this is going to be same deal. We need to take the derivative of f with respect to x, but f itself is going to be df dg, because g is going to be the next variable that we're working off of. It's the next shape, the next form inside of the function. We could also replace the variables with something that just is easier to understand. So dg dx. But, again, g is not in the form of x, at least not in its easiest form. It's now df dg times dg dh. Yep. Times dh dx. And again, h is not in the easiest form, so we're going to just copy all of that. Copy all that, put it there. We're going to move dx over a space, and again, make this dh dj dj dx. Alright, we don't like that either because j is not in the form of x as the simplest thing, so move it over dj dk times dk dx. Oh, would you look at that? K is not in the form of x at its easiest either. So we take dx, we shift it over one more. It's dk dm times dm dx. And now m is a direct function of x. Okay, good, we're done. Right, so this is the chain rule. We keep chaining the derivatives together of different forms until we get a direct function of x, or whatever variable we're using. And that's the one that we can stop. Right, f is a function of g, g is a function of h is a function of j is a function of k is a function of m, and m is a function of x. If you can decompose it, you can break it down into as small pieces as you like. So do something that's more comfortable than whatever nonsense is written in front of you. If you particularly like the large nonsense that's written in front of you, then you could probably just go ahead and take a direct derivative of x of this weird compound large function, but you are more likely to make mistakes. All right. Right, that's the chain rule, and the next one is the inverse function rule. Now, I did have this at one point in my classes. The question really becomes, when was that? Right, it should have been at the end of that chapter. Approximations, differential form. Okay. I'm going to go off of a proof that I wrote in 2022. Alright, so the inverse function rule says that our original function f of x, right, we're going to start with what is the definition of inverse of x? Well, or inverse of f. It's the inverse of f. It's literally, we're just using reflexive rule. Okay, what use is that? No, hang on. Right, if we take f of both sides and we don't simplify both sides, x is going to be equal to f of f inverse of x. Everybody happy so far? Right? Like, this doesn't change much. It's pretty obvious. Now, what we want to do is say, okay, if we take the derivative of both sides, we're going to get radically different results. Because the stuff on the right, we don't know what it actually technically is, and the stuff on the left is super easy. That's 1. Right? Stuff on the right, we're taking the derivative of f. F is a function of f inverse, which is a function of x. So instead of simplifying again, what we're going to do is we're going to say, okay, look, we're taking the derivative of the outer function, which is f prime. It's a function of f inverse of x. Then we have to multiply by the derivative of the stuff on the inside, f inverse of x. Right, and now we shift this to the other side. So the derivative of f inverse of x should be equal to 1 over f prime of f inverse of x. And so here's the thing. We can't necessarily say that this works for like all possible functions and their inverses, and it can't always work for every single value because not all of them can be plugged in. Right? It only works on the domains upon which it only works on the domains upon which it works. So it needs to be domain restricted. You need to be careful. I just went through ads, didn't I? No, I didn't. Okay. So we've still got 2 minutes and a little bit. These do need to be domain restricted, so you do have to watch out. But the idea that that the book wants to get across is that specifically this works at any point for which it works. Right? So if f has a non-zero derivative at x0, if then y0 is equal to f of x0, is a valid derivative for f inverse. Right, so we end up working with that stuff up there. Okay, I think we're going to stop here for tonight and get out before the ads come. So, apologies, but nonetheless, it ends up working out for us here. So, thank you everybody for coming. We're going to get going out to somebody who's professionally, preferably doing some educational type stuff, even if it's not necessarily math. I want to thank everybody for coming on in, and we're going to be back maybe tomorrow for either Elite Dangerous or something else kind of cool. Or we'll be back in on Friday for Against the Storm. So we'll see how things go, energy levels and all that. Anything else that's going on with the family. But I appreciate all of you. Thank you all for coming so much. And we'll see you next time. My name's Obi-Wan Pez. This is N Simplex Pachinko. Let's go see Rhaekodactylus. Have a good night.